Okay, I think we're ready for exploring the solar system part 2, how we explore the solar system using spacecraft. When I thought about this talk, I thought it would probably be worth just introducing how many spacecraft we have sent out into the solar system, and for whatever reason, whether it's to look back at Earth or whether it's to look at the moon or whether it's to look at the more distant planets. And I thought, how many spacecraft have we sent out there? There's obviously, and I started counting on my fingers, and then I thought, well, actually, there's an awful lot of them. So I'm going to describe here how we get out there into the solar system, what we do then in terms of how we get images back, and again, I'll ask the question, what is the next step? But the total number of the total number of spacecraft that we sent is, well, huge. I know you can't read that, but that is the last 70 years of sending spacecraft up. I've actually missed out one or two here because Artemis is going to the moon fairly soon, we hope. So you can see there are hundreds, literally hundreds of spacecraft that have been sent out to explore various parts of the solar system. How do we actually do it, for instance, for Mars? If that's the sun and we on Earth are in orbit around the sun, if we want to get to Mars, okay, this is not quite to scale, but this is just to make the cartoon a little easier to see. If we want to leave Earth and get to Mars with the minimum amount of fuel, we actually take what appears to be quite a long route to get there. But it turns out that's a very easy route because we can coast all the way. We just have to fire a rocket to leave Earth, and then we coast all the way until we get to Mars, and then hopefully we can land on Mars. So the actual way we get there is an orbit. It's an elliptical orbit where the closest bit to the sun is the Earth-Sun distance and the furthest part from the sun is the Mars-Sun distance. This was worked out a long time ago, and this almost certainly is the way we're going to get to Mars if we decide to go. And this is the way we've been sending rovers. If we send astronauts, it'll be pretty much the same thing. If you've ever seen The Martian, they've always been talking about this transfer orbit to get from Earth to Mars. It is actually called the Hohmann transfer. It's the standard way of doing it. But what about getting to other planets in the solar system? Well, in the 1960s or thereabouts, it was realized that if we want to go to the outer solar system, we can use the gravity of one planet to slingshot us onto the next planet. As long as they are in the right part of the sky, we can use a little orrery to check where the planets are, and then we can actually use this so-called gravity assist. As we go past one big planet like Jupiter, it can literally give us a push and send us on to the next planet. If we do it right, if we get the timing right, we can launch from Earth with a relatively small push, in other words, a relatively small rocket, not using much fuel, and then when we go past Jupiter, we can get it to slingshot us further on, and then when we pass Saturn, we can get it to throw us past Uranus, and then when we pass Uranus, we can get it to slingshot us to Neptune. The planets have to be in the right place at the right time, but the opportunity arose in the 1970s to do this, which is how Voyager 1 and Voyager 2 got to explore essentially all of the outer solar system, Jupiter, Saturn, Uranus, Neptune, 4 planets for the price of 1, using the gravity of each planet to throw you on to the next one in the sequence. Using gravity assists, you can explore the outer solar system faster because you get an extra speed boost to get you there, and it's cheaper because you don't have to take as much fuel because you're using gravity to accelerate you, not fuel in your rocket. So it's cheaper and faster, a double whammy. This is one of the first images we got back from another world. Any idea what it is? Any guesses? If I tell you which particular spacecraft gave us this image, Luna 3. So you now know what it is. This is the first image of the far side of the moon. Remember, one face of the moon always points towards Earth. The far side of the moon never points towards Earth. So if we're confined to Earth, we'll never know what the far side of the moon looks like. Hence, in the 1950s, satellites were sent to the far side to take these images. Let me clean it up a little bit. We can take some of the noise out. You can see the resolution isn't fantastic, but this is the 1950s we're talking about here. Remember, this is before the age of digital cameras. So how did they take images when you haven't got a digital camera? It was film, emulsion, for those of us who remember film before it became digital. Film was exposed to the image, and then the film was developed, and it was fixed, and it was dried in a little chemical laboratory inside the spacecraft. Then the negative was scanned by a flying spot, a cathode ray tube electron spot, was scanned across the negative, and the amount of light that passed through the negative was recorded by a little photomultiplier, which converts light into electricity. And then the signal from the photomultiplier was transmitted back to Earth so they could regenerate the image. A bit like, with apologies to the youngsters, a bit like how fax machines used to work. And fax machines, of course, are now old technology. So the fact that you can take emulsion and expose it and develop it and scan it and send it back to Earth was essentially the only way it could be done in the 1950s. We now have much more sophisticated ways of doing it because we have digital cameras which effectively take the light and immediately convert it to a signal which can be sent by radio back to Earth. And the Lunar Reconnaissance Orbiter, back in 2009 here, some 50 years later, also imaged the far side of the moon. Notice, A, it's much higher resolution, but notice also it pretty much got everything right. Back in the 50s, okay, resolution not as good, but they got all of the dark and the light areas in the right places. The so-called dark seas, the mare, these basalt lava flows, everything was mapped out correctly. If we move forward to the 1960s, Mariner 4 was the first digital camera. And I mean the first digital camera not on a spacecraft, I mean the first digital camera was built for spacecraft. You have a digital camera in your phone because that is the granddaddy of all digital cameras. It was built so that we could take digital images of planets. Mariner 4 had the first digital camera strapped to its underside there, and the imagery, the data from that camera was recorded on tape. As it flew past Mars, the data was recorded on the tape. Once it had gone past Mars and was flying in the distance, many millions of miles further on, then they replayed the tape and transmitted the information back to Earth so that Earth could then say, that's what you've just been photographing. Various craters, again, we can clean it up a little bit. So this is the mid-1960s. We can now verify that Mars has got craters, very much like what we're looking at directly above your head there. And of course, we can verify that there don't seem to be any canals on Mars. It just seems to be a cratered surface. We've now visited essentially every major body in the solar system. We've visited every planet. We've actually visited quite a lot of the dwarf planets and other objects that are floating around inside our solar system. I'm not going to dwell on all the details, but let's just have a look at Cassini. This is a spacecraft that went to visit Saturn. It was exploring the rings of Saturn, the surface of Saturn, the moons of Saturn back in 2004, and it lasted for quite a few years until it was finally crashed into Saturn in 2017. When it comes to the end of its life, why do you bother crashing it into the planet? Why not just leave it orbiting Saturn? Well, there is the outside chance that the moons of Saturn, just like the moons of Jupiter, appear to have oceans, and it is just possible that there is life in the moons of Jupiter or in some of the moons of Saturn. If there is life out there, we do not want to contaminate those moons by having a spacecraft crash into them accidentally. So to make sure the spacecraft didn't crash into a moon centuries hence, at the end of its life, they crashed it into the surface of Saturn, which we are fairly sure cannot harbor life. I'm not going to go through all of the numbers here, but it gives you an idea of just how many commands were sent to this spacecraft, how much data came back from the spacecraft. Hundreds of gigabytes of images were sent back from the spacecraft back to Earth. Here on Earth, we can look at Saturn and we can get some wonderful detail of what's going on in the rings, for instance. But if we send a spacecraft, we're so much closer, then we can get so much more detail at what's actually going on there. Cassini was able to show just how much detail there is in the rings and verify that the rings are basically lots of tiny particles all independently orbiting around Saturn. And there's also a few very odd rings that seem to be a bit lumpy. And there's a few moons embedded in there called shepherd moons, which are responsible for keeping the rings in the sort of structure that they currently have. The more detail you look from Cassini, again, for those of us of a certain age, it starts to look like the grooves of a long-playing record. And the more detail you look, the more detail you see in all of this structure within the rings. The ring system, hundreds of kilometers in diameter, but possibly only a kilometer or so thick. The rings of Saturn are probably the thinnest, relatively speaking, the thinnest things in the solar system. When the sun was glancing across the rings rather than down or up onto the rings, the sunlight cast shadows. There were bumps in the ring, and you can see from the shadows, the jagged shadows here, there seem to be little bumps and mountains. These are more than a kilometer high, perhaps, but it tells us that something is not perfectly smooth in the ring system, and people are looking at these sorts of images to try and understand the dynamics of how all of these particles in Saturn's rings are moving. Cassini was able to take an image that we will never get from Earth, and that is Saturn with the sun behind it. In other words, if you fly the spacecraft very carefully into the night side shadow of Saturn and look back, then you get the sun shining through the rings. So in other words, the rings are now backlit. That is very useful for scientists because when light is traveling towards you through something, you can see how the light gets scattered. That tells you how big are the particles that are scattering the light. So it's very useful to get an idea of the distribution of particle sizes within Saturn's rings. Whilst it was there, it also had a little interloper, an extra passenger, which was the Huygens space probe, because although Cassini was there to look at Saturn, the Huygens spacecraft was released to go into the atmosphere of Titan. If you remember, Titan is the one where we're thinking of sending a helicopter. Well, Huygens has already been down there. It was just a very simple lander. It wasn't supposed to be a rover to look around. It was literally just throw it into the atmosphere, let the camera run, and see what it sees on the way down to the surface. Titan has a very thick methane-based atmosphere, and this is what Huygens saw as it went through the atmosphere before it finally crashed onto the surface. It tells us that although Titan is only a moon, it still looks like a rather fascinating world. It saw rivers, it saw mountains, it saw what looks like liquid flowing down into lakes, it saw clouds, it saw rain. So there's an awful lot going on Titan, and it's well worth another visit, either with the Dragonfly helicopter or perhaps some other probe in the future. So as Huygens came in, it saw this rather interesting world, but it was simply drifting down on a parachute. It couldn't go exploring anything. It was literally just, let's see what we see on the way down. Another mission was called Juno. This was a mission to Jupiter. In this case, they decided that unlike the rovers on Mars, they couldn't afford to have a thermoelectric generator on board. They had to rely on solar panels. Jupiter is quite a long way from the sun, so they had to have pretty large solar panels to pick up enough power to power this particular spacecraft. Again, I won't go through all of the details, but again, huge amounts of data coming back from Jupiter. Terabytes of data, in other words, thousands of gigabytes of images coming back from this spacecraft back to Earth. And what it did was effectively go on a big orbit and fly close to Jupiter and then away, and then close to Jupiter and away. Look at the amazing images it saw as it took this skimming over the top of Jupiter sort of approach. Notice the little white flashes occasionally? That's lightning in the upper atmosphere of Jupiter. You see the flashes come and go. Clearly, there are some very stormy clouds on Jupiter. It's now passing over the top of Jupiter and then looking back as it flies off into the distance. We have some odd-looking white spots, which are storm systems. Some of the storm systems on Jupiter have been raging for hundreds of years. Why is it that storms on Earth last for a few days and then dissipate, whereas storms on Jupiter can last for years or decades or centuries? Why is that? There's interesting color changes. The equator of Jupiter looks a sort of salmon-y color, but when we look towards the poles, we get an interesting blue color. That is telling us something about the chemistry of what's in those clouds. Is it ammonia? Is it sulfur? Are there other molecules or elements present? These sorts of space probes will be looking to see how these planets are put together. When you look in detail, it starts to look not so much like a planet as much as an impressionist painter or watercolors that have been left out in the rain. Some of the structures we get when we look at the clouds of Jupiter are pretty amazing. They're trying to work out what this dark spot in the middle is. They think it might be looking deeper into the clouds of Jupiter. And again, trying to understand why the clouds have different colors, why there appears to be a differentiation between clouds at different heights. Literally just trying to understand, if you like, the weather on Jupiter. We should remember that the solar system, the orrery over there, 8 planets, etc., but the solar system is not just the Sun and 8 planets. New Horizons is a spacecraft that's gone even beyond Pluto to explore what else is out there beyond the 8 planets we know and the dwarf planet Pluto. What else is out there? We know, for instance, that even within the solar system there are at least 300 moons, and we know that beyond Pluto there are thousands, if not millions, of other objects floating around out there that might be worth investigating. But if we just think about those 300 moons, some of them are very interesting and circular, a bit like our moon, a globe. Some of them are more potato-shaped. The smaller ones tend to be rather irregular. So we have potatoes and we have walnuts. It seems like we've got Star Wars Death Star as well, looking at that one there with this huge crater on one side. But there are a number that are particularly interesting. These are the largest moons in the solar system. Again, for reference, there's our own moon. Notice how Titan, the moon of Saturn, is actually bigger than our moon. And notice how fuzzy it looks because it has this thick methane atmosphere, which makes it very difficult to see the surface. That's why we sent the Huygens probe in there to see what's going on. But Jupiter, as well as having this moon called Io, which looks more like a pizza than it does a moon, also has these other moons which are very interesting looking. Europa, Ganymede, Callisto. These are 3 of the 4 moons that Galileo first saw in the early 1600s. They are a topic of interest because we think those moons, although they are described as icy moons because they're covered in ice, we think that under the ice there are oceans. If there are oceans with chemicals and a heat source, that is precisely what life needs to get a start. It needs a liquid, preferably water. It needs minerals and molecules, and it needs an energy source of some kind. And we think that the oceans of these icy moons of Jupiter could, in principle, harbor life, which is why the European Space Agency has sent the mission JUICE, Jupiter's icy moons, and NASA has sent the mission Europa Clipper. They have both been launched roughly a couple of years ago. They're on their way to Jupiter. In a few years' time, they'll arrive at Jupiter. They'll be studying the icy moons, and maybe we'll get a few clues as to whether or not these oceans definitely are where we think they are, underneath the ice caps, underneath the ice crust of these moons, and is there any way we can tell what's going on in those oceans? Before I finish, let me just make one comment about, okay, it's all very well saying we're going to send these spacecraft and we're going to get the images back, or we're going to get this data back, but how do we get the data back from these spacecraft? Well, it's usually done by radio. That is still the most efficient way of doing it at the moment. Basically, you have a radio transmitter on your spacecraft. It, of course, takes a certain amount of energy. You need to drain your batteries to send a radio signal from your spacecraft over millions of kilometers, at which point it gets picked up by a huge radio dish here on Earth, large enough to pick up the very weak signal from this spacecraft millions of kilometers away. That is how it's been done up to now. But a relatively recent mission sending a spacecraft to an asteroid, they said, let's do a test. Is it possible to do things better than sending them via radio waves? Can we do it with lasers? Can we do it with light instead of radio? So they had a test. As well as sending radio transmitters on the spacecraft, they also sent lasers. And that laser, instead of coming down to a big radio dish, is picked up by a big optical telescope, a telescope that points at the spacecraft and hopefully picks up the laser light coming from the spacecraft. In principle, lasers can transmit more information per second. That's why we have fiber broadband, because optical fibers with lasers going down them can carry more information than you can get simply over radio signals coming to your house, for instance. So they thought they'd do a test. Okay, we're going to send a whole load of data back by laser. What do you use as a test? Well, ideally, not just an image, because that's too small. Let's take a nice, big, high-definition video lasting a few seconds and transmit that and see how fast we can get that data back to Earth. We're sending data on a laser, so what video should we send? Why don't we send a video of a cat chasing a laser? That's a great idea. So NASA basically sent this video of a cat chasing a laser back from a spacecraft, and when the spacecraft was 50 million kilometers away, they got a data rate of 260 megabits per second, which is faster than some people can get on their broadband from a transmitter that's 10 miles away. But this is 50 million kilometers away. And even when the spacecraft was essentially on the other side of the solar system at a distance of 400 million kilometers, they still got a data rate of 8 million bits per second being transmitted on a laser. Generally speaking, much higher than you can get with a radio wave, perhaps 1,000 times faster than you can get with radio. So it's still transmitted at the speed of light, but the amount of information you can get in a second is much higher. So in future, when we send spacecraft out into the solar system, it might be possible, we're not using lasers routinely yet, but we've now established the technology does work, it might be possible to get that data back from the distant part of the solar system back to Earth much faster than we are doing at the moment. So again, don't worry about making notes of these web pages, but if you're interested in any of these missions, there is currently a mission that's going to explore Mercury. That is going to be in orbit in a little later this year. Cassini is now no longer because it's been crashed into Saturn. New Horizons is on its way out of the solar system. Juno is still in orbit around Jupiter, and these Europa Clipper and Jupiter's Icy Moons missions are on their way to the moons of Jupiter. If any of those you want to know about more information, then go and have a look at those web pages. There are handouts here if you want to go and explore for yourself. Thank you very much.